so linear programming problem number 3. Let's read and see if we can understand. Toys A Go makes toys at Plant A and Plant B. Plant A needs to make a minimum of 1,000 toy dump trucks and fire engines. Plant B needs to make a minimum of 800 toy dump trucks and fire engines. Plant A can make 10 toy dump trucks and 5 toy fire engines per hour. Plant B can produce 5 toy dump trucks and 15 toy fire engines per hour. It costs $30 an hour to produce toy dump trucks and $35 an hour to operate that sentence doesn't make sense, but I think they mean $35 an hour to produce the toy fire engines. How many hours should be spent on each toy in order to minimize cost? And what is the minimum cost? Okay, so we're going to start off the same way. How many hours should be spent on each toy? So we're going to have number of hours spent making dump trucks and making fire engines. Let's say D is number hours on dump trucks, and F would be number of hours on fire engines. Okay, so there's my two variables. Let's think about the constraints here. We have a lot of things going on. Can I go into negatives? No. So, already I know that D and F have to be greater than or equal to 0. All right, let's see what else is going on. I have 2 plants. One plant is Plant A. They can make 10 dump trucks, 5 fire engines per hour. And Plant A needs to make a minimum of 1,000 of those 2 together. So that's going to set us up like this. Plant A can make 10 toy dump trucks, so 10D plus 5 fire engines, and they need to make a minimum of 1,000. So I need this to be greater than or equal to 1,000. Does that make sense? So there's Plant A. See if you can do the same thing with Plant B. They need to make a minimum of 800 toys altogether. They can do 5 dump trucks and 15 fire engines. Hopefully you came up with 5D plus 15F greater than or equal to 800. Have I lost anybody so far? Well, go back. Where did I lose you? Good thing, well, you'll have this video to rewatch. Okay. I don't have a ton of time, so let's see how far we can get. I've listed all my constraints. We're going to worry about the cost when we do our objective function. We'll go ahead and graph these. So on one side, I'm going to have let's see here. Let's see how far we can get. All right, so I want if I just quickly look at the scale here, let's say, which side should I have as which? D. Yeah, these are going to be my number of dump truck hours. Fire engine. Okay, if I have to graph these here, let's quickly see how high we need to go. 10's going to turn into 10 times 100, and that's going to be 200. So I got to go up 200 there. 200, 800 divided by 15. Yeah, it looks like I need to go up to 200 on each side. So maybe I'll count by 10s. Maybe I'll count by 20s. Okay. All right, now we'll just graph our constraints. So I'm in the first quadrant, so that takes care of D and F both being positive. If I plug in 0 for D, I get out 200 for F. So 200 on F, 0 for D. And then if I plug in 0 for F, I get out 100 for D. So I'll connect 200 to 100. Then 800 divided by 15 is, oh, it doesn't come out nice. Well, that's annoying. 53 1/3. Ugh. If I plug in 0 for D, 53 1/3. I'm going to mark it here, 53 1/3. And plug in 0 for F, 800 divided by 5 is 160. 160. So I'll connect these two. So now what's interesting about this one, your feasible region is not down here. Because look at your inequalities. You want it to be above these values. Right? I want to be above both lines. So that means my feasible region is this. So my ordered pairs are going to be here, 0, 200, here, 160, 0, and then also here, but we ran into a snag because it's not on a nice spot. How do you figure out where exactly that point is? Yes, you have to solve these two equations and see where they intersect. All right,